GM. Morning, good afternoon, good evening, good night for everyone out there.
Good afternoon.
Hello, hello, hello. Welcome everyone for the lesson 21. Finally, we are getting closer to the last weeks of this bootcamp. I have just 4 lessons of content to go over, and then you're going to get a new perspective with the workshops next week with a lot of different protocols and different presentations. And then you are ready for your final project. Have you decided what you're going to build already? What kind of the app you want to do, or what theme you want to explore? Oh, let's meet next week. It's the special guests week, the sponsors and the partners of Encode. We are going to have a lot of presentations. I won't be teaching, so you're going to be released from my bad jokes for next week. You're going to have new, fresh perspectives from all the presenters for you to build your final project in the last week, in the 8th week with the group. Yeah, time flies, right? I also need my to rest my voice a little. Starting to sound weird, weirder than usual actually, but I'm going to be back at the last week. I want to see all of your presentations in the last day of the bootcamp. Okay, so I'll be there. But let's not get ahead of ourselves. We still have 1 week to go. Today I have the scaling solution for discuss the scaling solutions, and we're going to see that these solutions are not that much of a solution at all. We're going to discover this today. And I also selected some contents that we didn't cover in last lessons in the last weeks. A few of them, I'm going to pick them today about assembly, about libraries, because it's going to be important for this week. Tomorrow we speak about DeFi, so decentralized finance, how to integrate protocols like Uniswap or Flash Mints and this kind of stuff. On Wednesday, we're going to speak about upgradability patterns, how the smart contracts can be upgraded and how to deal with them. And last but not least, on Thursday, we're going to see IPFS, a decentralized storage, peer-to-peer network for decentralized storage, and a security toolbox for us to use in our bootcamp, for no projects for this bootcamp and for all the projects next, because we didn't have much time to cover security, so I need to give those extra tools. And that's it. We covered the last branches of this bootcamp so that you can decide on what you're going to do on your final project. Okay? Excited? Let's get started with blockchain scaling solutions first. Understanding the scalability trilemma and getting to know some of the solutions. And today we're going to zoom in one solution that would be the bridges, but there are many other solutions out there. Okay? First of all, let's do some discussion. Like we did last week, we first discuss about the problem, we see it happening, and then we propose a solution, right? Have you ever made a payment with blockchain before? Paid for food or bought an item or something like this? Maybe one or
No,
two volunteers.
no,
Dante,
no.
you have made, right? We are not going to collect any information for taxes or whatever here, okay? It's a safe
Mhm.
environment. So how does it compare to making a payment with traditional payment methods, for example, Visa and MasterCard? What are your takes on this? Maybe I use you as an example, Dante.
Well, uh, I mean, it has been through both through a centralized exchange with a debit card, where it's So I used to have the FTX exchange card, and
Oh,
when I spent the FTX card, it would sell whatever token I said, I attached to it.
I
And
hope
then
it
I've
didn't lose
also
money
used,
there.
yeah, and I've also used where you actually pay with Lightning, you know, um, or something like that. And it's pretty much um the same thing. I would say the speed is pretty much the same with Lightning. I've used I think Arbitrum as well, and Solana. So the speed is pretty quick. It's basically the same thing. So it's just I guess a different method, whereas one is with a actual card, the other one's probably with a phone. So
Nice. Plus, you have the added network security of the blockchain and the decentralization, right? So you see those primitives coming in, the speed of the transactions and all. But also you have very slow payments, like if you try to pay people in Bitcoin or if you try to pay people in Ethereum mainnet, it's going to be costly, it's going to be slow, right? And most of the discussions about blockchains, the surface level discussions about price going up, price going down, Solana versus Ethereum, uh, Base versus Arbitrum, and all, they usually battle, most of them, like 90% of more of them battle in this ground of speed, security, sometimes decentralization to compete, which is the faster, which is the best for the end user, which has a better UX and all, right? And whenever we see someone claiming my blockchain is the fastest or it has the lowest gas fees, we tend to think that they are the winners. They are more intelligent. They did something better. They worked more. They put more effort, and thus they are the winners, right? This is the way that usually those discussions go. Oh, you have a faster blockchain? You are brilliant. You are smarter than Vitalik, Gavin Wood. You are smarter. Even Gavin Wood forked and did Polkadot to try and compete. But also you see all of this discussion, right? Let's go beyond that today, people. Let me present you the trilemma. You probably heard about that already. That you cannot have at the same time. Let me pick a more modern article, like this one from Ledger Academy. Uh, this one is great. Like you cannot have at the same time uh, scalability, security, and decentralization. They would fight between themselves. Every time that you maximize for one of those, you lose in the other two. You're going to pick two and lose the third one. Okay. Let's put in simple terms. We're going to go eat out for lunch or for dinner. We can pick places that are cheap. We can pick restaurants that are tasty, and we can pick restaurants that are healthy. Sometimes we're going to find places that are cheap and tasty, cheap and healthy, health and tasty, but it's impossible to find a place that is at the same time cheap, tasty, and healthy, right? It's very difficult. So those forces, they fight themselves because it is a thing of reality. Okay? You're following? So the blockchain trilemma is the same thing. You have those three fighting factors. So whenever someone is claiming that their blockchain is faster, it's not necessarily because they are genius and they won the game against all the blockchains that are slower. It's maybe because they architected the design of their system, their blockchain, for being less decentralized or less secure. It is a design choice. Of course, you can make a blockchain that is centralized, unsafe, and slow at the same time. Yes, you can. So there is room for improvement. But also, when you are comparing apple to bananas, on speed, you might not be comparing what is underlying. And I like this old article from Gemini because it boils down to this theorem, the CAP theorem, back in the 80s, with blockchains that were in the 80s. None was blockchain we know of. And the Bitcoin that doesn't even have the word blockchain there was coined in 2009, right? So at the 80s, we didn't have any kind of blockchain, but still the computer scientists who had computers in the 80s, not one, right? People were living their lives, they were using newspapers, sending letters and all. Some universities had computers that were that odd thing in the wall that they thought that would be replacing the libraries, you know. So in the 80s, those nerds, those computer scientists, they came up with a theorem called CAP theorem, with which would articulate that decentralized data stores, which blockchains are an iteration of, but you can think of like Dropbox, Google Drive, any kind of, even your own storage, like where you keep your files, any kind of decentralized or distributed data store would only guarantee 2 out of 3 properties: consistency, availability, and partition tolerance. Pick 2 out of 3. This is not something that is invented or like a technological limitation that we can overcome by computing faster, something like that. It is a design consideration that has those implications about reality. Trying to solve the CAP theorem is like trying to solve gravity. A natural occurrence is like, let's make those planes fly. So let's invent a way to get rid of gravity. What? It's better to put wings on things and have them flying, right? So the CAP theorem is the same thing. It is a repercussion about nature of data, how data exists, how the logic of data exists, and you need to deal with it. Okay? Let's explain the idea. You can either have consistency and availability, consistency and partition tolerance, or availability and partition tolerance. Something that we saw when we were discussing the Taylor network with those oracles, remember? You cannot have 3 of them at the same time. Either I'm going to have a consistent information all the time. Imagine I'm dividing the same information in the United States, China, Europe, Brazil, South Africa, in Australia, in Chile, Argentina. I have the same information out there. So I have a lot of partition tolerance. For me to have consistency, I first need to call all of those places, call by phone, send an email, something like that. Hey, is that information correct? I put my name or my age, my current age. Every time that I visit a country, I put my age there. So I would need to lower availability, wait a few minutes, maybe a few hours for me to call everywhere. Is that information correct? Did Mateus go over a year and age? I don't know. So I'm calling all of the spaces. Okay, it's correct. And then I have consistency and partition tolerance, but I don't have availability. Or I have good availability. I look at that paper. I go for Argentina, I look at that paper. Oh, Mateus is 29. Okay, now I have high availability. But the data is not consistent because now I'm 33. I have some threads of white birds growing already. So this information was old. So you have good availability, you have good partition tolerance, but you don't have consistency. Information can be different from all the information that I have in the network. Or I can have consistency and availability by centralizing the information. You want to know how old I am, you call me, only me, nowhere else. So I don't have partition tolerance, but I have availability and consistency. You see? This is the CAP theorem. With this very solid realization, less than 15 minutes of lesson, we can dismiss most of the discussion out there in the web about which blockchain is the faster. Okay, because it is only depends on how they position in the CAP theorem. Okay, let's translate the theorem to what blockchains do. Decentralization would be the partition tolerance, how tolerant you are for decentralization or no. Security would be the consistency, how much you can have the same correct information everywhere and not have anyone to hack that or to change that. And scalability would be the availability, how quick you can change that information and make it be consistent and partition all over the world, okay? And let's read decentralization correctly, because scalability is easy for us to know. We send a payment, we want it to arrive now. We don't want to wait 2-3 days as the traditional banking system. We don't want to wait 15 minutes for a block confirmation. We want it now. We want to click and it happens now. When we open social media, we have that. So we know what scalability is. We can sense it very well. Security, well, not so much. We are going to know when there is a hack. We're going to know when there is a problem. We're going to feel. About decentralization, we almost don't feel that. It is a central ethos of blockchain. The peer-to-peer electronic cash system was invented because of decentralization. It still is the least desired, the least spoken feature for the end user in most cases, speaking about the masses and all. So how to measure decentralization for us? A lot of people measure this by the number of participants. This is not entirely true. Sometimes you have a lot of participants because you are paying for these people, you are attracting these people with centralized sources of funding, you are incentivizing nodes to be online with centralized funding, with your own money, with your own operation. And this is not a good measurement of decentralization. A good measure of decentralization, or more accepted to wider terms in the ecosystem, would be how easy it is, or how many barriers of entry you have, the opposite, for new nodes to connect to your network. So even though some networks, they have like 1,000 active nodes, they still can be more decentralized than all the networks with 100,000 nodes, which are maintained by central funding sources, okay? So how easy it is for you to go there and be part of that network, for contributing for the security of that network, or how easy it is for you to go there, plug your hardware, and contribute for the operation of that network, okay? If there are a lot of barriers of entry, if you need to have a super duper hardware with high throughput, with a lot of memory, you have lower scores of decentralization. You are more centralized. Only some people in the world are going to be able to contribute for that network. If you can allow anyone to plug their potato computer there with their Raspberry Pi and they are part of the network, you have a lot of decentralization. Anyone can be part of that. You have more resistant against censorship and all, okay? Even if you have 0 nodes, theoretically, you're more decentralized than all the protocols, you see? That would be the correct measurement of decentralization. And whenever we are discussing solutions for that, solving the trilemma, and this article is very old, like we don't call it Ethereum 2.0 anymore. No one is speaking about sharding, Yeah, this article is very old, but let's stop here. Solving the blockchain trilemma. There are no solutions. You don't solve gravity. You see, you design your system, your wings, whatever, to fly against gravity using some other factors. So whenever you are solving the trilemma, you are designing your network to deal with scalability decentralization, and security in different ways. And some articles, they do these comparisons of what the Lightning Network is doing, what Polkadot is doing, what Phantom is doing, what Cardano is doing, what Avalanche is doing, and they all claim that they have solutions for the trilemma. But when you go past this for half an hour with the cracked engineering mindset, you're going to see that it all boils down to how you position yourself in the blockchain trilemma. Okay, and many things that people call improvements are just design choices. For example, Ethereum improved in scalability when it moved from proof of work to proof of stake. So they are calling it an improvement here, which depending on how you measure is an improvement, right? In manufacturers, it is transaction per second, gas costs, and all. But then you would argue, now you need to have 32 ETH being discussed to flexibilize in the future for you to become part of the ecosystem. Who here has 32 ETH on your wallet? If you do have, maybe you don't want to review yourself. But you can say, oh, we can join a group of stakers and stake together as a whale. Yes, it's possible. Okay. So that is this argument against proof of stake. But in the same way, you could say, oh, but in proof of work, you not anyone has those big hardwares for mining ETH or Bitcoin or whatever, GPUs or CPUs or even ASICs, right? Well, that is the thing. For you to become a validator of Ethereum proof of stake, you would need to buy ETH, right? And the price in dollar per ETH is almost the same worldwide. You would, for example, in Brazil, you'd buy in Brazilian reals, in Argentina, would buy in pesos, in Europe with euros, but the dollar equivalent is quite the same, maybe 5% more or less, but it's quite the same, right? But think about mining. The price of electricity is the same in everywhere in the world. It changes a lot, more than 10x in some places. The price of hardware too. So in proof of work, you are incentivizing people that live nearby coal mines that are the cheaper electricity sources, the dirtiest electricity sources in the world, or some countries using like geothermal or something like that, for you to mine Bitcoin or whatever chain you are using proof of work, that you are staking electricity, staking hardware, staking your time for you to have that reward. So you see how it's very tricky to call something an improvement or not, because depending on how you measure, it is an improvement. But depending in all the directions, it's not an improvement at all. Okay. So this is the kind of lenses and mindsets that I have this list here. The Ethereum 2.0, we're going to see that we don't call it 2.0 anymore, okay? You would have sharding as the initial proposal, where you would be able to have parallel states of the blockchain, but it evolved to be something more like a collection of layer 2 chains, of side chains, chains that would be working by themselves, as they call here those nested blockchains or side chains, that they would live by themselves. You could be interacting with those chains entirely, and every time you want to go from a chain to the other, you would create bridges. Okay, there are a lot of examples of state channels too, where you start this channel from the state that you have in the main blockchain. You would do all of those transactions there in that state channel, and when the channel finishes, you would go back for the main blockchain state. The problem here, this is a great solution like the Lightning Network. We had Raiden, we had Lightning Plasma on Ethereum too. The problem is that you end up trusting in that state channel. Whomever made that initializer, whomever participated, could be the center point of failure, or that smaller group of people. So you still trust a smaller subset than the whole chain. The same thing for the side chains. The side chain, they don't start as a channel. They start with their own Genesis block, and then you can bridge from those two. We're going to study this design with more detail in a while. So in one chain, we can optimize for speed and scalability, like less decentralization, more speed, more scalability. And in one chain, you keep it safer, you keep most of your sensitive assets there, which is kind of similar to other solutions like, for example, Polkadot, funded by Gavin Wood, one of the founders of Ethereum 2, where you have cross-chain universe, a cross-chain protocol like Cosmos and other similar ones, where you have several blockchains bridging and communicating between themselves. It's just that they have more of the streamlined avenues for these communications to happen other than bridges. But it's similar to how Ethereum is going. Instead of having shardings, they are having now layer twos on top of that. And then you can list a lot, like Polygon, one of the first ones. That is Arbitrum, that is very big nowadays. That is Base. That is Celo, that became a layer two now. There are many others that use ZK, proof of stake. There are many different designs, all the OpStack, with optimism. There are many different designs that would allow you to have those parallel chains. The idea is that whenever you want something slow and safe and decentralized, you go for the layer one. Whenever you need something quicker that you can transact a lot and you don't care so much about decentralization security, you go for layer two. Similar to how we keep pocket change on our pocket, right? You have your money in your bank account, which is low to transact. There's a lot of security for you to withdraw. And now sometimes you pay a fee for withdrawing cash now. But when you have cash, you can quickly pay for things. In your credit card or in your pocket money, you can quickly pay for things. And whenever you collect a lot of money, let's say you are selling cupcakes, $5 per piece. You will make 100 of these cupcakes. You make $500 at the end of the day. I would be one of our customers, maybe, if I had $5. I'm hungry now. So in the end of the day, you have $500 in your pocket. You are going to go back home. You're going to pass in that dark alley. You see a risk of you being mugged, robbed. Someone could steal your cupcakes, which is not good too. So you go for a bank and you deposit those $500 there. The next day, you need to buy ingredients. You withdraw $200. You buy those ingredients. You make more cupcakes. This is life as you go, has been there since the invention of currency, of money. Banks are one of the oldest institutions we have in the history of humankind because of this very need. L1s and L2s are very similar to that. Whenever you want to go from a place to the other, you would use bridges. These bridges are systems that are designed for you to exchange tokens, for you to exchange information, especially financial information, from one place to the other. For example, from ETH mainnet to Arbitrum, layer 2, and back and forth. Okay. A very simple use case example of these bridges for you to understand would be the trusted bridges, which are not ideal, but just for you to understand and simplify this concept. You would rely on a central entity or system to operate this, and you would have some trust assumption. For example, you want to exchange ETH on mainnet to Arbitrum. So I'm going to tell, hey people, I have 1 million assets here on Arbitrum, and I have 1 million ETH of those assets on ETH too. You can transfer me your assets. I'm going to give you them in the other place. I'm a trusted bridge now. That's simple. And I charge 0.1% fee. A centralized exchange could be your trusted bridge. I'm not gonna lie, I did that a lot of times. It is practical. You want to exchange money from the alpha beta chain, the corner of the universe, to Ethereum. Instead of going through a lot of hoops, you can just go for an exchange, deposit that thing, sell for the other coin, and then withdraw the thing. That can explain a bridge, you see? Not ideal, but it can work. So, for example, trusted bridges, very easy to understand. I want to convert from one chain to the other, from ETH on mainnet for Arbitrum, for example. You can do that. The problem is that trusting other people, the main use case, the ethos of a blockchain, the main ethos of the whole thing is having decentralization, right? So why would we trust people for that? Doesn't make much more sense. So instead of doing the trusted bridges, which are very convenient, usually we have decentralized bridges or trustless bridges, which are not that trustless as we thought of, but they are a little more decentralized than just trust me, I'm a central exchange. You would have some central, you would have some smart contracts instead of the central player, and some algorithms governing those smart contracts where you could have proofs like zero knowledge proofs and rollups. You can have proof of stake networks incentivizing correct behavior. You could have encryption algorithms between those that eventually would operate those bridges in a trustless way. It's just that if the bridge is as safe and as decentralized as the main blockchain, how come it is that it is faster? We just saw that trilemma, right? So for a bridge, it should be faster than the chain you are using. It needs to be what? From what we saw in the trilemma. You need to give up a little of security or a little of decentralization. So this is why most of the hacks that happened in the story or in the history of blockchain, I guess, just lost by the Bybit hack that happened last month or 2 months ago, and the SBF FTX thing. If you just consider those, most of all the big hacks were from bridges that were hacked, like billions of dollars hacked. If you consider all of the bridges that were exploited, either by social engineering or by hacks, single point of failures, and all that happened in those bridges. Okay, not trying to scare you away of using bridges, just to explain what is this piece on the ecosystem and why we need them and how unsafe they can be in some places. Okay, so this explains the ecosystem, the scenario. And if you look on the roadmap of Ethereum, Ethereum is willing to become a place for cheaper transactions with extra security, with better user experience, and future proofing. So, cheaper transaction, extra security, better user experience, future proofing. What it's going to be less? Now you tell me. It's going to be cheaper to transact, more scalable, more secure. So what's going to be less? It's going to be more centralized, right? Are you asking for this link? Should we burn them to the ground because decentralization is the ethos of blockchain, blah, blah, blah. Wait, no, wait. Stow your pitchforks, your torches. This is a contribution of the ecosystem itself. The ecosystem of Ethereum is telling we want cheaper transaction, we want extra security, because we want to launch more meme coins, we want to make the exchange owners more rich. We want to make these investment funds more richer, and we don't care that much of decentralization. The ecosystem is telling that. Not saying that it's bad. It is an ecosystem decision, right? So if you want to be part of this from the each research, the magicians and all, you can be part of it. Okay. So this whole roadmap, this whole path that Ethereum is taking, it's because of how the community wants. And if you want a more decentralized version of Ethereum, you might want to fork it, you might want to create specific projects for that, because this is not the will of the community. Okay, the community want to maximize for cheaper transaction access security. It's possible to do that without giving up decentralization. Little improvements, yes, but according to the trilemma, it's not possible to gain advances in those other two without giving up decentralization some form, even if it's a little. Okay, and we also don't have this ETH2 anymore. Okay, they use it to call that, but we don't use ETH2 anymore. You would say that the ETH1 would be the consensus client, and the new Ethereum would be the Ethereum client, the execution clients, okay, how they would work. And it's mainly focused on the L2s. We don't have charging anymore. We have all of these layer 2 roll-ups and now, which would have a much faster roadmap other than the charging itself. So they remove that to favor, since the merge, update of proof of stake with the beacon chain, more just 1 second. They wanted to be more focused on this layer 2 map. Okay. So any questions up to here on what we see of scalability, the trilemma itself? Next step would be showing one example that would be Polygon, doing one example in the LG transaction. Before we get hands-on, any questions, any conceptual questions up to here? No? Maybe raise your hand if you have. No, okay. So let's keep going. I will pick any project that we did in the past. For example, project 6 or any project where we deployed a token. And I created this folder for the lesson 21. It's going to be for today's lesson and everything that we have here. Okay? I'm going to show one example of using Polygon layer 2, but you can abstract this for any other layer 2 in Ethereum or any other bridge operation that we would do in other blockchains. Okay. The idea is that whenever we do a transaction in Ethereum, big Etherscan here, closing some tabs. Whenever you are doing a transaction in Ethereum, you need to be bound by this block time. These blocks that happens at every 15 seconds or so, they can only carry up to 200 transactions. So like 10 transactions per second, something like that. It is very slow if compared to Visa, to MasterCard, or anything like that. So if we want something faster, but we still want to use our assets in Ethereum, we would need to go for a layer 2. Polygon is one of those solutions where you can connect your wallet. Let me connect my MetaMask wallet that I have here. Not in overall Polygon. In this portal, Polygon, we can have many other wallets that are compatible. Even MetaMask, Coinbase wallet, they have that inherent now, these bridging functionalities. So if I want to go faster than Ethereum using my assets that I have in Ethereum right now, I can, for example, connect my wallet that I have those assets in Ethereum mainnet to this wallet that I have here. Let me approve the signature. Let me connect here. Okay. I'm using the testnet version of it here in the bottom. You can switch for mainnet. And I'm going to do a bridge. I'm going to pick assets that I have in Sefolia. For example, Sefolia ETH. And I'm going to transact 0.01 ETH to Polygon Amoy testnet, which uses a proof of stake, or Cardona that uses a zero knowledge proof. Those two different ways for securing those different blockchains. And then we would have an estimate time of 22 minutes for this transaction to be completed in the other side. But when I have it on the other side, I can spend it back and forth very quickly. Like withdrawing money from the bank, I need to go for the ATM, I need to put my information there, I need to get the cash and paper and go back home or whatever place. This usually take half an hour or so, 10 minutes maybe. This would be a similar process, okay? If something goes wrong with Polygon on their side, you can always recover your funds in the layer 1. So it is a link. Sometimes you can recover it easier. Sometimes it's more difficult. For example, we had a layer 2, the public good network, GN layer 2 to Ethereum, I guess. Yes, public good network. It was layer 2, but depending on the way they would implement, depending on the bridge you did, you would need to bridge the funds back, and then they phased it out this layer 2. It was used mostly by Gitcoin now. So depending on the design, you would have more security or less security on this bridge. But in this idea, I would have 0.1 Sepolia ETH when transferring to Polygon. I would have that 0.1 rapid Sepolia ETH on Polygon. Okay. So this is another detail. Some layer 2s, they use ETH as the native token, like Base. And then you can transact with the ETH that you're transferring. Some others, like Polygon, they use a token called Pol. Used to be Magic, but now it's Pol. So you would need to buy Pol in Ethereum and bridge Pol there for you to use as a network token. Because even if you have ETH in Polygon, you cannot pay gas with it. You would need to have Pol tokens for paying gas with it. You see, so this is where the confusion starts for the new users and all. You will need to buy those specific tokens to transact there for signing transactions. Okay. Then I can bridge, I would wait a while, and this would complete. Okay. Now for using those blockchains at the other side, I have one example here of a script similar to any other scripts that we have used in this bootcamp, where I'm going to use VM directly without hard hat, using VM to connect with this custom RPC URL. Okay, and I can use Sequoia here, just like we did in the previous lessons of this bootcamp. Okay, I have it configured on my computer in this folder. Okay, I have put all of the contracts that I'm going to use for today's lesson already here in this folder. I've put all of the scripts that I'm going to use here already. So I'm going to show that, but if you need time for coding that on your side, just let me know. I'm going to wait. For now, you can pick any of those projects that you did in the past. Like you would have this RPC URL somewhere in your M file, and you can run this script as I'm going to run now. Okay. Ask it a terminal window, but I'm not seeing it. What's happening? Let me open this on Cursor. You can open any of your previous projects on VS Code and Cursor too for being the same place as I am. And I'm going to see how quick, how easy it is for configuring a layer 2 for configuring your connection for a layer 2 using VM. And again, this is not just about Polygon, can be any layer 2 in Ethereum, would be something very similar. Okay. So I have my .env here, as you would have in similar lessons from this bootcamp. And I have this script test layer 2. That is exactly the script that I have in the README. This script here. Okay. And I have a custom RPC URL that I'm going to pick this custom RPC URL that is in my .env. I have it there, I promise. The same one that we used in previous lessons, in the lesson 8, if I recall. I guess we used that in the tokenized ballot, maybe. We used that for deploying an Oracle too with Tello. And all of those RPCs, they are connected to some providers like Alchemy, Fura, as we had as a homework in lesson 4, remember? So that we could connect to a blockchain. Let me run that script now. Just to show what I have. It's nothing very different to what we did in previous lessons. Okay. Okay, compiled. Wait, forgot to rename one thing. Change would be Sepolia. We discussed on RPC URL. Okay, sorry about that. I'm using the same script here, but I had something different. So change Sepolia custom RPC URL, and we are going to change it later. Forgot to undo those changes. Sorry. Now I have this script. I did something wrong, but whatever. So this is the last block number. And this is the deploy address that I had. I guess it's a well, yeah. Sorry. Again, third time's the charm. Forgot an A here. Sorry about this. Third time is the charm. So now it's working. So like we did in previous versions of this script in the bootcamp, I'm connected to that block number. This is my address and this is my balance. Normally, we did that a few times. It's nothing new, right? Connecting to an RPC node. Whenever we are using a layer 2 with this money that we bridged, with those assets that we bridged, we would change from this RPC URL to the URL of the chain that we want with another RPC provider, or we could run a node of that blockchain if it's easy enough. For example, a Polygon URL or an Arbitrum base, wherever. You go for Alchemy, you go for Infura, and you pick the endpoints for that RPC. You would have it there. If you want to do that now, I can even wait for a few minutes. You go there, pick, you go there, for example, for Alchemy dashboard, and then Alchemy portal, Alchemy blockchain. Sometimes it gives other results. So you go there, you log in, you go for your keys, and you're going to see that one of the possible keys that you have there would be for Polygon, for example. Get your API keys and go there. Not advertising for Polygon, you can do that in any other chains. You go for a dashboard, any other chains or any other providers, you go for the dashboard, you're going to find those chains there. I did that already. It is in my .env. Okay, so I have this custom RPC URL in Polygon. Okay. Browse, this is Alchemy. Remember on lesson 4, you had that homework of doing the RPC providers. You should have some of those, okay? So I have it here on my environment, the custom RPC URL for Polygon. I'm going to use that now for making those calls. And I'm going to configure VM for using the chains of Polygon Amoy. That would have the correct token name, Matic, they would upgrade to Evolve eventually. We would have the correct addresses for everything. So if I change lines of code here, change Polygon Amoy here and here, and if I pick this URL that points to Polygon, now when I run the same script, could be deploying a smart contract to tokenize a ballot, casting votes, whatever you did in the past in this bootcamp, now can be done on this layer 2. I'm in another block with the same address, but now I have a different balance. You see? So any of your previous script in this bootcamp, deploy a smart contract to Ethereum, blah, 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 you can now do in one of those layer 2s. What if I want to bring those assets for layer 1, and then you would have a bridge? What if I want to bridge data, call a smart contract from another chain, and now then in Ethereum this is a little more tricky. Okay, you would have protocols like CCIP, cross-chain communication protocol from Chainlink. You would have all the kind of protocols that you can send messages, that you can trigger all the executions and all, or you could coordinate that in your own backend, do this execution back and forth. From there, in the front end, the user could be interacting, okay? For the end user, this is kind of a nuisance because when I'm used to the traditional finance network or the traditional applications, we don't, as a user, we don't care what is happening under the hood, which network I'm connecting to, which gateway is processing that. We just care that our payment was completed and we have that balance. Now I have that transaction done, right? Whenever we push that to the end user, it is kind of a pain. It's kind of a nuisance for the end user to deal with that. I know. It's just that for the sake of decentralization, we need to. But if the user is not caring about decentralization, they can use whatever less decentralized version. They can even use a centralized app, and that would work, right? Okay. And this concludes the explanation about scalability. Yeah, question, Arthur?
Yes, so our custom RPC URL is supposed to be from Polygon MOI?
Yeah, you can pick it on Alchemy, Fuda, whatever chain that you prefer, and
But for the Polygon
whatever
MOI
provider,
network,
whatever
right?
in Polygon Boy for this exercise. Okay. I use Polygon as an example because it was there like 4 years ago when I started teaching these kind of things. I had a project deployed on Polygon like I guess 5 years ago now. Time flies. 2020, right? Yes, almost 5 years. Dang. So I use it because it was there when I started teaching the things, but now we have plenty of other layer 2 options. Arbitrum, Base, most commons out there. You have all the blockchains with layer 2s. You can even use another layer 1 as a bridge, as a off-chain. There are protocols that envision that by default, like Cosmos and Polkadot, and there are protocols that are not, like Solana and Ethereum could bridge between those two. Okay, there are layer 2s that there are layer 1s that becomes layer 2, like Celo. Celo was a full-fledged layer 1. Then they joined it Ethereum ecosystem back as a layer 2. There was Flow that became closer to the Ethereum again. So but they still have their layer 1. So the whole fracture or not fractured scene of bridges depends on those protocols, and unfortunately not always they are being 100% technically transparent with the end users about this kind of competitive edge that they have on scalability, when actually it's just a trade-off. Okay. I guess that concludes the tone for today's lesson. Having an engineering point of view of that discussion, you're not going to discuss transaction speeds anymore without knowing what you are comparing on the hood, right? Okay. That concludes the part one of today's lesson. 1 hour gone, half an hour to go, where we go for those other contents here for encoding, libraries, assembly, each of those 10 minutes or so to explain where they came from, what is going on, and then we finish today's lesson. Okay. No questions? Slow Monday today, maybe. You shy? Did you have a snacks? Remember to hydrate. I'm taking a lot of water to see if I kill this flu. Yes, Dante.
So, in the .env, what do okay, here it is. I see it. Never mind. I had to scroll up a little bit, but
And this
I got
one here.
my RPC from Alchemy for Polygon, and I'm gonna put it under which of the three. I already have my private key, but the other two, would it go under
This
the
one, the
whole?
middle one would be for Sepolia, and the third one would be for Polygon.
Okay.
And then you can switch those quickly just by changing this line, or with RPC URL or RPC URL Polygon.
What line was that?
Like the line 13. Like I did here, I can quickly change from this to that, you see? Pointing at Polygon, pointing at Ethereum, pointing at Polygon, at Ethereum, you see? And also you change the line 17 and 25, just for having the correct numbers there. Those two changes that I have in the region. Okay.
Thank you.
Good, good. And just as an extended context, we have the proof of stake version of Polygon, the original one that they started as the sorry, that they started as the Matic chain at the time, then became Polygon, the original proof of stake, and then they also added a ZK EVM, a zero knowledge roll up, where you don't need to stake money to become a validator now, because now you can prove things with the ZK proof whenever you want to prove that you had this asset there, that you want to bridge it back and forth, you can use zero knowledge for doing that instead of waiting for the convergence for everyone in the network. Okay, and the security goes up, the decentralization goes up, but also the scalability is a little lower. The amount of things that you can do decreases. The amount of roll-ups that you can do depends on the throughput and the one and all the nodes need to be beefier. Okay. And bridges, not always these bridge books, okay? The transaction can fail, and after you wait 22 minutes, you should see the end assets there. This is how I got those 0.22 that I have, 0.20 that I have. It was bridging, okay? If you try with Cardona, I guess it's more, let me see, it should be quicker. 0.1, 20 minutes, okay, 2 minutes quicker. Okay. And then I would need to approve that. Wait for confirmation. That would take a little while.
So the balance you had was from before, so it didn't happen today.
No, yeah, I did that before. I bridged it
Okay.
like a year before, something like that.
Yeah, it's telling me the transaction is still waiting, but it doesn't show a transaction hash or whatever. Obviously, it didn't happen.
Yeah, it's going to land on the destination blockchain after a while. After this period finishes, okay? Dante?
Okay, so how do I configure VM for Polygon Amoy?
You are in this step? Yeah, so
Yes.
you have the same script as I put in the readme, right? Just make sure you
Yes.
are on the same page. Maybe I went to this quick too fast. You are going to change the custom RPC URL as we have here. Okay. And every time that you have change dot whether you're going to change for change dot polygon, polygon boy. Every time that we have this thing here, you see, we are going to change from
Yeah,
change
which
dot
is
Sepulveda.
you said 13, then 17, then 25. That's where I changed that, right?
Yeah,
Okay.
and that would configure VM for polygon. Okay. Good. So that would explain later. It's not even 1% of the whole discussion. I guess you got the point. Like whenever we speak about a subject, it's more like an introduction to that subject. When we spoke about gas optimization, it's just introduction that this whole field exists. When we spoke about security, just introduction that this whole field exists. And now we are speaking about scalability, just introduction that this whole field exists and how the discussions would go. Much more the number goes up, numbers go down. That is a discussion about network security and architectural designs. Okay, good. Any questions about implementing that, troubleshooting, please feel free to open issues on the GitHub or ping me on the technical questions in Discord, and we can get this through. Okay. Question about that, Dante?
No, I just want to say I got it to run in it had my address and the it had 0 pol in there, but I guess that was the point of it, to be able to connect to that RPC and that wallet.
Yes, and if you get poll item from the faucet, as we have here, get tested tokens from this faucet, or by bridging, and then you can find this balance out there. Okay, good,
Cool. Thank you.
wonderful. Yes, Browns. It is this exact step as we have in the bridge me here. Okay, change to use Polygon Amoy. Okay, this is step here, but don't worry if you have questions, issues about this, just ping me. I can guide you through slowly or later. Now let's give a look on those advanced contents. I want to explain about string manipulation, something that we saw on the lesson 2 and 3. Remember comparing string with the other by using libraries. Because first of all, libraries are very cool, interesting for using for things we're doing in the smart contracts. And this ability of doing libraries is very cool, but also we're going to use delegate call in the future in this bootcamp in the lesson 23 Wednesday when we speak about upgradability patterns. So it's interesting to stop and give a look on these libraries, explanation how it works for us to prepare later. Same thing about assembly that we're going to see today. And we even mentioned that in previous lesson when doing that signature example with the lottery, remember? So there are very common libraries like this one and these ones that can be used for utilities, string manipulations, and many other utilities. And the idea of those libraries is that whenever you deploy them in the blockchain, they are stateless, the code is there to be reused later in the EVM, and you don't need to deploy that smart contract again and again when you are going to implement that library. So imagine that you can pick 10, 20, 25% of the smart contract size and put it there in a library for being reused later for many other smart contracts, saving some good gas deployment and creating some interesting mechanisms on chain. Let's do one example with this strings library. This is a library created by James. All the credits for him. This is a library that is going to give these kind of functions like concat, like index of. Let me open that in Cursor. I have it here in my contracts folder already. So this library strings, it's going to give those functions like concatenating two strings together. The library needs to be stateless, so I don't have any string here in that smart contract for me to concatenate. Everything is going to be passed as pure functions. Okay, I'm going to receive two strings and I'm going to return one string with those two concatenated. I'm going to have a function called concat. Find that split, no, pair, no. Okay, I thought I had it. Maybe that's the first one. Sorry, compare. Concat is the first one that I explained. The other one is the compare. Sorry about that. I have it here somewhere. Split, no, compare. So I can pass one string and compare to the other by doing a loop. If the lengths are different, I can know that they are different, but if they are not, I'm going to do a loop for every member of this array, going to every member of this other array and comparing them one by one. If I'm comparing two books, and the difference it is in the last character, the last byte, this is going to take a lot of time. Remember, we saw that last week. So when using this library, and I have a test here with the string comparing two versions of this smart contract, two versions of the usage of this smart contract. One using ABI itself, for example, ABI encode. What is that? Inside the specifications of ABI, now I have those references here. References. Should have done a better job organizing this in the correct. Here, inside the specification of the ABI, we have those methods that would be encoding and decoding of parameters, function selector, argument encoding and decoding, where I could pass a byte and or a string and all, and that would go for the encode and decoded. There are ways to pack things. For example, this encode pack and encode unpacked, that would pick a lot of different variables. For example, an integer, bytes, a uint, and a string would pick all of those bytes and I would join them all. And then when I need to go back from this joined array back to the variables, I need to know where one started and where one finished. Otherwise, I don't know what belongs to what, right? So these kind of operations are baked in the API specification. The API is able to do that. The EVM, when computing calculation, has access to these functions, okay? The API is used for a lot of things. We can use it out of scope, for example, for doing concatenations, like doing like this. Or we can concatenate using the library. And this is one thing that I wanted to point for you. When I'm using the library, I don't necessarily need to pass the two parameters, like concat, and then pass string 1, and then string 2. Okay. Libraries are meant to be attached to types like this, using string for using the library strings for every string that I have in my code. So the function concat is going to receive the string s1 as the first parameter, and the second parameter is going to be whatever I have inside the parentheses. If I had 3, 4, 5 parameters, the first one would be what is behind the dot, and the next ones would be the second, the third, and the fourth would be whatever I have inside the parameters that I'm passing. Okay? This is how the library is intended to be used. And whenever I'm doing a concat, I'm copying the code of the library and executing the context here of that smart contract when doing this concatenation. Okay. Which brings us all of this smart contract definition that we have here. We're going to test this function concat and the function compare. Here, we're going to test those two against the ABI. And I have a script for doing that. So you can just copy this script and put there in your scripts folder. And I have it here with this strings test. Okay. Maybe you want a few seconds for doing that. I'm refill my cup of water to do this. And if you have questions, let me know. Okay.
While you're doing that, could you go to your Polygon dashboard and check transactions?
Polygon. My transaction failed too. If that's what
Yeah, I
you're
mean-
asking, Arthur.
Yeah, isn't it supposed to say at least pending transactions?
Yeah, my transaction failed. I don't know
Yeah,
if it's going to show. Actually, it's pending here. Good.
Yeah, I tried like 4 times and nothing even is pending, so I'm sad.
Well, I don't know, but you understand this is about this application. It's not about the whole architecture. I guess if you abstract away Polygon and if you replace by any layer 2 of your preference, you're going to understand it better. Okay.
Oh, mine actually went through. It spent like 0.1 ETH from my Sepolia, but I don't see it on Amoy or anywhere else.
They stole your money.
They really did. It doesn't even show in the transactions now.
Yeah, yeah.
The hell is
But
happening?
I would suggest you to focus less on Polygon and the Polygon portal and focus more on the architecture. Use this just as an example. Okay. So in this script, putting here as a string test, whatever, we are going to do some operations. For example, I'm going to pick this contract and concatenate and save using the library. This is string B and the string A. String B is apple and string A is pen. And then I'm going to have apple pen. And then I'm going to concatenate string A and B again using the API encode to compare the gas costs of them. And then I'm going to do a comparison with string C and A. String C is pineapple and string A and pen. I'm going to have pineapple pen here. Why those words? Those are just random words out there, not related to any famous YouTube video, right? You have the reference. So in scripts, I'm going to test the string tests. So you know that you have those two kind of operations for you to do. And sometimes the strings library is going to be better. Sometimes the API is going to be better. And for example, using comparisons between pen and pineapple using the library would cost 33,000 units of gas, and using this same false comparison with the API would use 29,000 gas units. And when we join pen, pineapple, apple, pen at the end, and we compare those two big strings together using the library, it costs almost 87K. And testing this true comparison with the API code is only 74. So you see why we use the data on lesson 2 and 3 for comparisons. It is indeed cheaper in all of those scenarios, even when having different lengths like pen and pineapple. It would be very easy to determine that those strings are not equal because they have different lengths. Just because of the array conversion, we have much more gas being spent using the library than we have by comparing the hashes. We didn't have much time to do that on the week 1. And now we have, and we learned about libraries in the way. For us to view more about libraries, I want to show you this assembly test, which is not a library, but where I got that from. I guess I had someone suggesting that as a library. Wait. Wait a minute. Yes. Sorry, that was the but I'm not using it as a library anymore, so whatever. For example, they suggest this library get code art for us to understand what is assembly doing here for us. Okay, so libraries would be a way for us to call any address here, for example, and then we can ask what is the code at that address, for example, and would receive an address and then would do these operations. Okay, I'm going to explain assembly just in a while. Before we proceed, about libraries here, we use those two ways using the API methods for comparing and concatenating versus those methods of the library, and we saw the difference between them. Okay, so whenever you want to do strings operations, you can either import this library or you can use the API directly for doing those comparisons. Okay. Okay, browse. The command is just running the script string test. Okay, then you copy. You should have the smart contract, and you should have this smart contract in your contracts folder, and you should have your script there correctly for it to work. Okay, that would demonstrate the use of those libraries. And this library strings is a canonical library present in the testnet version that we're using here. We don't need to deploy that library first. If you want to test that get code at library, this is not a canonical library. It's not present, for example, in the Red Hat local testnet. It's not present in the Ethereum testnet and all. You would need to deploy that library for using it in your smart contract. Just a small difference, just to highlight that. So moving forward, assembly. Whenever you want to do things that are not natively supported by Ethereum, by Solidity syntax, for example, let me pick the code out again. For example, retrieving the size of a code inside a smart contract. This would need assembly. There is no function in Solidity that would retrieve the size of a code of a smart contract. That is a function to retrieve the code, but not the size of the code. You would need to do something like that. Okay, just to contextualize, we saw some things like this in this bootcamp. For example, in the address.sol utility that we have in OpenZeppelin, when we are here, when we are checking, this is something that is implemented in ERC 721, for example, 1155, when we're checking if a smart contract is if an address is smart contract or no. For example, we can have those assembly blocks. This is a smart contract present in production with OpenZeppelin utilities. You have this assembly operation doing this. So it is the easiest way to do bubble reverse, the reverse region using memory in assembly. What is that? It's using another programming language inside Solidity, inside this assembly block called Julia. We call this language is a bit lower level than Ethereum, than Solidity itself. It is more like brushing bytes because you use those statements like swap, dump, jump, mem, and all directly, but it's still you would work a little above bytecode level yet. It wouldn't be like assembly level, bytecode level, but it's still it gives you more control than Solidity. Okay? What's the best way to visualize that? For example, you can program an ERC20 similar to this on token ERC20 in Yule, just like you would do in Solidity using this kind of code. You see here how we have those method IDs, those function selectors. So this would be the selector for balance of. This would be the selector for total supply. And then when I implement those functions, for example, total supply, allowance, owner, total supply. Total supply is just loading from storage from a position in the storage that I'm storing that variable. Whenever you do a Solidity code, under the hood, it is becoming some operations like that. So you can be more effective in the amount of gas you're using. You can protect against some security breaches and all, the more control you have. In lesson 23, we're going to see one example of assembly for doing proxy calls. So just remember that assembly exists. Is it going to be part of the homework project to write assembly, something like that? No. This is just to know that it exists, okay? For you not to be taken surprise when you see that in practice. And there are advanced bootcamps for that with Encode if you want to check. So a code reference, I'm doing this contract called assembly test that I'm going to have a function get code add that is going to be called from this smart contract to get the code from itself, the deployed code on itself, okay? And we're going to execute that with this test script. I'm going to deploy that assembly test, and then I'm going to read the get this code. Okay, let me run that. So it's going to run this assembly test with this script test assembly. So I'm going to deploy this contract assembly test, and I'm going to get this code to get the contract on this address, the address of this smart contract that is calling right now. And this is going to return something for me, this bytecode. So let me run that. Yes. Add run scripts, and then I'm going to pick test assembly. So even though I didn't write a Solidity code for this, when this smart contract is compiled, these are going to be the instructions that are going to happen. I'm going to pick the size of the code stored in that address. I'm going to store it in memory, in some positions, store the length of it in memory, and then retrieve the code in memory, and then return that for the return statement here, this memory code. And look how this is interesting. I can use a variable that was in Solidity, like code equal to 0x, something like that, 0x00. I need to do bytes array, right? So it would be a little more complex, but I can do maybe I can do like that. Byte this and 0. Um, uh, it is in memory, whatever. I could even use a variable in Solidity for doing whatever I want, pick it from memory, blah, blah, blah. And then I can use the same variable inside my assembly, like I'm doing here in line 15, is the same variable as I have in the line 9. So I can dance back and forth in those two realms when doing my implementation. And if I call that inside that smart contract, the smart contract was deployed, and this is what returned from the output. Byte code of the contract, 0x 60, 80, 60, 40, 52, blah, blah, blah. I could return that with assembly. And this would be the same byte code as I have in my artifacts here for assembly test. If I pick the JSON, if I pick the byte code, 60, 80, 60, 40, 52, ending in 33. Or, yeah, ending 0033. Ending 0033. See, somehow inside the blockchain, don't know if you paid attention, this is a call from inside the blockchain. This is a call for VM to pick the get this code call in EVM, in hard hat runtime environment that computed this, that used this assembly block to compute that. Okay. So this is doing assembling inside a smart contract. You have low-level calls for things inside that smart contract. So for example, I want to retrieve a variable that is an internal variable from another smart contract. We don't have any way to do that in Solidity, normally using those interfaces. But I can code an assembly code easily that reads, do a memory read, a memory load, read, whatever, that specific slot in that smart contract. And if I know that that slot is that variable, I don't need it to be public. I can read. Everything in the blockchain is on my reach now. I can't write to do this storage without having the permission in that account, but I can read. Anything is possible to be accessed and loaded using these calls. Okay, so nothing is private in a blockchain, not even the private variables. Okay. And this is it for today. I guess this opens or understanding that the EVM is quite bigger ecosystem than what we have on the powers of Solidity. We haven't mastered not even 10% of Solidity itself yet, but we should know at this point that beyond Solidity, there is a much bigger field that would be the working on the EVM itself. Okay, and there is where most of the gas optimization partners would lie. Most of the security problems, the breaches, and all, they live beyond Solidity only, and they can be addressed. They can be solved by using this kind of assembly blocks. They even put some examples here in the README. If you want to give a look on those. The signatures on chain would use that. If you go for ECDSA, so at the line 53, we would have this assembly block here, like we used it in last week. Okay. This is it for today, people. Scalability, libraries, assembly. That's good for a Monday. Tomorrow we keep with it. Thank you. Have a good one. Bye-bye.